Here we've got a projectile, and it's going to be fired up with an initial speed of 200 meters per second at an angle of elevation of 45 degrees. And there's a number of things that we're going to compute with this. We're going to find the range of the projectile, the max height reached, and the speed at impact. And I've gone ahead and sketched out the scenario here as best I can. And the components that we're going to be looking for particularly again are the maximum height, which will happen here, and the speed at impact, which will happen here. And of course we also wanted to figure out range of the projectile, and the range is this distance here. Now when I work with these particular formulas, and I'm going to go ahead and write them out, I generally write them out and use them more parametrically than anything else. I think it's just easier to sort of separate out the I and j components into effectively their horizontal and vertical pieces. So this is the horizontal, and y of t then will make the vertical component, and that looks like v0 sine theta times t minus 1/2 gt squared. That's our vertical. And they've given us the initial speed here of 200 meters per second, so we can sub that in for v0 here and here in our formulas. We know g is 9.8 meters per second squared, so that would make x of t equal to 200 cosine theta, and we also know that theta is 45 degrees, so this is going to be 45 times t. Y of t is going to be equal to 200 sine theta, which again is 45 degrees, times t minus 1/2 gt squared, again using 9.8 to represent our gravity. And lastly, let's go ahead and complete that simplification here. So x of t, again that horizontal component is going to be 200 times cosine 45, which is root 2 over 2. So this is going to be 100 root 2 t. And y of t is going to be, again, sine of 45 is root 2 over 2. So this is 100 root 2 t minus 1/2 9.8 t squared. Half of 9.8 is 4.9 t squared. So now we've got our horizontal and vertical pieces of our position function here. So now we can start answering some of these particular questions. So the first thing we wanted to do was to find the range of the projectile. So the range, again, being the distance here from where it's initially launched to where it lands. And the thing that we want to make a note of is that when it lands, its height is 0. So what that would indicate to us then is that our vertical component, or our height, would be equal to 0. And what that'll allow us to do then is solve for the time at which we hit the ground. At that point, I just need to know how far it went, which is the horizontal component. So we will solve here for t when it's equal to 0, and then we'll take that t and plug it into our horizontal distance function. So let's work through that. I get 100 square root 2 times t minus 4.9 t squared, and set that equal to 0. And how we go about solving this isn't particularly important. We need to just get those values, and from there we can then again find that t that's appropriate and plug it in. So when you do that, you get a couple of values here. We end up with t being equal to 0, which would indicate that's when we launched it. And the other t is equal to about 28.86. And I'll call it seconds because that's what it is. So now that we have that t, we can plug that value again into our distance function here for x of t. Again, this is telling us the horizontal travel for any particular time. So we want x of 28.86. And plugging that in and evaluating that through, well, 100 square root 2 times 28.86 is equal to 4,081.42 meters. So this is approximately how far that particular projectile has traveled. So that answers the first part of that question, which is what's the range? The second part of the question is to find the maximum height reached. And although this is still a parabola and we could look for that vertex, we're really intended here to use our equations for projectile motion to determine what this is. The key here is recognizing that when you're at this particular point, something's happening vertically. The object has to go up, it will stop, and then it has to come back down. So right at this particular point where we have our maximum, that's really where the velocity vertically is equal to 0. So what we're looking now is at that vertical component, y of t, and we need the velocity that's related to that change in position to be 0. So that would indicate that we would want to find the derivative, y prime of t here. So let's get y prime of t. And let's just make a little separation here. Now we're looking for max height. So y prime of t is going to be equal to 100 square root 2 minus 9.8t. Again, the idea here is that that velocity, that vertical velocity, has to be 0 at the point where we stop from going up and switch to going back down. So we'll set that equal to 0. And again, this will allow me to solve for the time at which that happens. So the time here is about 14.4 seconds. And again, now that we've got that time, just like we did before, to figure out the actual max height, we need to go back to the position function for the vertical component and use that time there. So if we plug in t for that, we end up with y of 14.4, which is going to be equal to 100 square root 2 times 14.4 minus 4.9 times 14.4 squared. And evaluating that through, we get 1,020.4 meters. So that would represent then our maximum height. Now for the last part of this, we're asked to compute the speed at impact. And there we're going to need the magnitude of the velocity, which of course is just the sum of the squares of the individual components there. So I'm going to need this velocity vector v, which for me is going to be x prime of t and y prime of t. Fortunately, we've already found y prime of t. That was up here. So it is just 100 square root 2 minus 9.8t. And x prime of t is just the derivative here, which is going to be 100 root 2. So now we can form that magnitude. So this is going to be the square root of 100 square root 2 quantity squared plus 100 square root 2 minus 9.8 t quantity squared. And then we just need to simplify that down. Or realistically, because we're doing this at our particular time, that is, we're doing it at the time of impact, we could just plug in t equals 28.86, which is the number we found, or our time that we found earlier for that impact. You'll remember going all the way back here, we have the number for that particular time that we used for the range. So we can take that 28.86, and really before simplifying, we can just evaluate it in here for our velocity. And what that will give us is 199.989 and some change here. And what that really works out to is effectively 200 meters per second, which ironically, or maybe not, is the initial velocity that our projectile was fired at. You'll remember all the way back here at the beginning of the problem, we had our initial speed of 200 meters per second. With these problems, we often neglect air friction, which effectively means as long as we're starting and finishing at the same altitude, the velocity going out is the same as the velocity when we hit the ground. The other thing that we might actually catch on to a little bit is, again, because this is projectile motion, you'll note that we had our time of impact was 28.86, and the time we had our max height was 14.4, which just happens to be half of that total time traveled. And again, that makes sense. This is a regular parabola. We're neglecting air friction here, so the thing travels in a regular curve. So we would expect actually that this particular vertex for the parabola would happen halfway between the two x-intercepts. So those things are just nice to correlate and check, just to make sure that we've got it solved out the way that we want. So just again, a good way to check your work. That is what we expect. But again, the idea here is really to apply these formulas that we're learning and get a little bit of use out of them that way.